fellow mathematicians. Welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And we're here to suggest that mathematizing is not about mimicking or rote memorizing, but it's about thinking and reasoning, about creating and using mental relationships. We're all about empowering teachers and students and parents and everybody to empower them to think and reason mathematically. We answer the question, if not algorithms, then what? All right, in today's episode, we're going to highlight the commutative property and how it can make some mental computation really cool.
Mm-hmm.
Okay, so when kids start to solve problems using counting strategies, because that's what they first do, they're solving problems, they use counting strategies, they get really literal and they always start with the first number. They sort of act out the problem. And so that means they're going to act it out in order because that's what makes sense to them.
Yeah. So for example, if you had a problem like Javon had 4 pencils, she found 8 pencils on the floor and picked them up. How many pencils does she have now? Kids are going to often solve that by starting with those 4 pencils in the problem. And then we're really, really happy when students realize that they can count on from the larger number, starting with the 8, because then they have less to count on.
Yeah, sure enough. So instead of a student saying, okay, 4 pencils, and now I'm going to pick these pencils up, 5, 6, 7, and sort of keeping track of those extra 8, a student can just start with the 8,
Right.
8, 9, 10, 11, 12. And all they have to count on less. They just have to count on 4 instead of counting on all of the 8. And so counting on less makes sense. We kind of want to bring out that with students. Kim,
Right.
What are some ways that teachers can encourage young students to construct this idea, help them construct the idea of counting on from the larger?
Well, first of all, they just need to know that it's a thing, right? So that's one reason why we share strategies. So I feel like we'd solve a problem and I'd have one kid share who did all that counting on, starting with a smaller number. And then I'm going to invite someone to share who saw that they could just start with the 8 and just count on 4 more. And I would celebrate hard how sophisticated their thinking was and ask the students to consider which one they'd like to do next time, right? So there's also some times where you may need to be even more explicit. I was thinking about a few years ago when I worked with a student who was struggling to move from counting on to using relationships. And we were doing some individual work. And I found it really interesting when I was kind of poking around a little bit to see where some of his gaps were. One of the things that I realized was that he wasn't ever counting on from the bigger number. And the reason that he wasn't doing that was because he didn't yet trust that problems like 4 plus 8 and 8 plus 4 would give him the same result. He didn't see that they were equivalent. For him, and maybe for some of your students, it's helpful to see that equivalence of problems like 8 plus 4 and 4 plus 8. So I would absolutely have my rec and rec or my number rack out and ask, what does a 4 plus 8 look like? And then for an 8 plus 4, it's just that same number rack flipped over, right? So if I have 4 on top and 8 on the bottom to represent 4 plus 8, then if I flip the rack over, that's going to represent 8 plus 4, 8 on top, 4 on the bottom. And those are equivalent. They can actually see no beads have been added or removed. They're just arranged differently on top and bottom.
I mean, that's a really nice sort of visual, concrete way for a student to go, okay, I'm totally clear that I've represented 4 beads on the top and 8 beads on the bottom. And if I just flip that rack upside down, now I have that other problem that I don't yet trust is equivalent, but I can kind of now sort of experience the fact that it's equivalent. That's a nice idea, Kim. Well done. Well done. Cool. So that's the commutative property for addition, that a number A plus a number B is equivalent to the number B plus the number A. A plus B is equivalent to B plus A. And since A plus B is equivalent to B plus A, you can solve either problem because they're going to have the same sum. And so you might want to choose which one that you're going to solve. So a problem with bigger numbers, where this comes in, let's talk about more complicated problems that could be really nice, is anything plus 99. So like if I have anything plus 99, I can think of that problem as 99 plus that anything. So for example, if I say 24 plus 99, then I might want to use the commutative property instead of thinking about 24 plus 99 to think about 99 plus 24. Why, you're asking? Why would I want to think about 99 plus 24? Because 99, 100, then I could think about 99 to 100 and then just add what's left over. I was supposed to add 99 plus 24, But since 99, 100, I've already added 1, then I just have 23 left. And what is 123? It's just 123. So the problem 24 plus 99 becomes 99 plus 24, which is just simply 100 plus 23 or 123. So there's some really maybe times where we don't even really acknowledge we're using the commutative property that can come in handy when we're adding numbers.
Yeah, as long as we're open to the idea that I would rather solve that 24 plus 99 as 24 plus 100 and then back up 1, because I really do like the over strategy.
I will never forget when you told me that one day. I was like so excited about being able to give and take and this idea of 99. And you're like, well, actually, I like to over those, which is totally reasonable, right? Totally cool. You can completely do that. And it's a great relationship. But yeah, it's not as much of my go-to. But yeah, we will allow that. No problem. I had a feeling you would say that. Okay, so Kim, what's another place where using the commutative property might come in handy?
So if our listeners were available last week, they learned about the swapping strategy for addition, and that's based on the commutative property of addition as well.
Right. So in episode 22, we talked about the swapping strategy. And in case people didn't catch episode 22, although you really ought to go listen to it, it's pretty great. Can we remind us about the swapping strategy a little bit?
Yeah, sure. So that's like when you're given a problem like 59 and 92, and you want to just rearrange the place values to create an equivalent problem. So like 59 and 92 could be rearranged to create a problem of 99 and 52.
And then you can sort of do either one of the two strategies that you and I just talked about, right? Because now you have 99 plus anything. And so 99 plus 52 is delightful to solve. Cool.
Right.
All right. What's another commutative property gem?
Oh, probably one of my favorites. So 10 times anything can be thought about as that many tens. So like, go ahead.
So sure enough, so instead of thinking about 10 23s to find 10 times 23, I can think about 23 tens.
Yes.
That's like 23 in the tens slot and no ones left over, right? So if I'm thinking about 23 tens, then I sort of put 23 in the 10 slot. I have 0 ones left over, and that's where the 0 shows up. So 23 times 10 is 230. I could also think about that like if I was thinking about 10 times 23, especially a beginning student might think about, okay, I need 10 23s, 23, 46. I don't even know what comes next. Like they're thinking about literally 10 23s. But if I'm thinking about 23 tens, then I can think about 10, 20, 30, 40, 60, and I can count by 10 23 times. Well, then I can kind of do that in big chunks, big jumps. Like if I need 23 tens, I could think about 10 tens is 100. So 20 tens is 200. So 23 tens is 230. Like I can make sense of this times 10 thing in our number system much better than saying add a 0 slash that. Don't say that. It's much more about thinking about how many tens we have. So that's a brilliant time that we can use the commutative property to sort of think about the number of tens instead of like 23 tens, instead of thinking about 10 23s.
So Pam, what if I asked you to find 23 times 99?
So find 23 99s. Yuck. Okay, cool. So this is a little complicated. Hold on to your hat because I'm actually going to use the commutative property twice here. So the first thing when I think about finding 23 99s is that I don't really want to find 23 99s. I actually want to find 99 23s because I think that's going to be easier for me because 99 is so close to 100. If I can find 100 23s, then 99 23s will just be one less 23. Okay, so I'm going to focus on finding 123s in order to find 99 23s. So that's the first time that I use the commutative property. But now, just like we just said, in order to find 123s, I don't actually want to think about 123s. I want to think about 23 hundreds. And 23 hundreds is just the number 23 hundreds, right? It's like 23 times 100 is 2300 or 2300. So I've sort of used it twice. So now that I have 123s, I can think about that as 2300s. I think about 2300s as 123s. And so then I can find 99 of them by just getting rid of 123. That might be a little confusing, but I sort of use the commutative property twice in there in order to find 99 23s rather than 23 99s.
That was really well said. And it might give our listeners a little bit of insight because you're so able to verbalize that, a little bit of insight into why the commutative property is kind of complex and not just, hey, do this thing, kids.
Yeah, especially if we just decide, all right, I'm going to tell you what the commutative property is, and I'm going to write an example on the board, and I want you to memorize the name of it. So we are not suggesting that. That doesn't work. It doesn't give kids the flexibility that you just heard us using in all these examples. What we really need to do is help engage kids in the problem-solving process and share those strategies and use problem strings to build the commutative property and use concrete examples like flipping the number rack, or with multiplication, we really want to be able to represent multiplication on rectangles, because then we can rotate those rectangles, and we can notice that if I have a 23 by 99, that's going to have the same area as a 99 by 23. So some of those visual models are going to be really important in helping kind of concretely build that commutative property in students, so that then we can use it in examples like we just used. All right, so I've got a finale for us today, Kim.
Okay.
All right. So in episodes 20 and 21, we talked all about percentages. We played with percentages, and we threw out lots of percent problems. We actually had an ulterior motive in there, an ulterior motive where we kind of had a goal, because, it's us, right? There's always a bam in there somewhere. There's always something that we're kind of leading towards, something that we want to be able to refer back to, or something that we want to be able to kind of keep listeners engaged, keep them on the edge of your seats, trying to figure out what our next bam is going to be.
So yeah, let me list a couple of those problems and answers and see if maybe you notice a pattern, maybe one that has something to do with the commutative property. So we asked 12% of 50, 50% of 12, and those were both 6. And we also asked 45% of 10 and 10% of 45, and those were both 4.5.
So we have some equivalent answers. What's going on? All right, so in percents, there's a multiplicative relationship between the whole and the percent. So is 10% of 45 really equivalent to 45% of 10? Yes, because 10 times 45 is equivalent to 45 times 10. Whoa, that is so cool.
It is so cool. So here's a really cranky problem. Would this be one that you would want to use the commutative property, and that would make it really nice? What about 67% of 20?
Okay, so since I know it's a thing, since I know I can choose to do 67, I can find 67% of 20, or I can choose to do 20% of 67. Since I know that's a thing, since I have that choice, because I understand the commutative property of multiplication, I'm going to choose to do 20% of 67 every time.
Right.
Because I can find 10% of 67. That's just 6 7/10 or 6.7. Then I can double that, because that's 10%. So double that to get 20%. So double 6.7, that's just 13.4. Double 6.7 is 13.4. And so 20% of 67 is 13 4/10, or 13.4. In other words, I can now look at a percent problem, find some percent of a number, and I can ask myself, do I want to find that, the thing that's given to me, like 8% of B, or do I want to use the commutative property to find B% of A?
So cool.
So let's try another one.
Okay.
All right, so I'm going to try to find a problem that it won't really help to use the commutative property, and we'll just sort of see how that goes. So
Okay.
Kim, how about 82% of 19?
Oh, that sounds awful. 84% of 19. So I know it's
Dun,
a
dun,
thing
dun.
that I can do 82% of 19 or 19% of 82. Those are my choices.
Mhm.
And at first glance, they don't seem really nice, but you know what? I would rather swap here, because I would rather solve 19% of 82, because I can
83.
find
Oh, 82. My bad. Sorry.
82.
I already forgot
And
the
then
problem.
that's okay. So I could do 19% of 82, because I can find 20% of 82 and then get rid of the 1%.
Oh, nice. So instead of finding 82% of 19, you're going to find 19% of 82 by finding 20% and getting rid of 1%. Okay, cool.
Yep.
So I tried to come up with a problem where you wouldn't want to use the commutative property, but you still did. Let me see if I can make it even harder. So we started with 82% of 19. What about 82% of 17?
So 82% of 17 or 17% of 82. You know what? 82% is not bad, because I can just do 2%, 4%, 8%. 80%. Like double, double,
Ooh.
double times 10. So 2% of 17, 4% of 17. And I'm not going to actually throw out the numbers right here, but the strategy that I would use is double, double, double times 10 to get the 80%, and then just tack on the 2% to find 2% of 17. Did you follow that?
Nice. Yes. Yes. Totally cool. Well, okay. Let me give you another one. What about 83% of 17?
That one's not quite as nice. 83% of 17 or 17% of 83. I think you've got one. I think that's a nice problem, but we can just chunk some pieces just like we've done before, right?
Sure. It's just that maybe neither of them are pulling at you to use the
No,
commutative property
no,
to
I
go
think
either
either
way.
way. Uh-huh.
Whew. Okay. Cool.
So we've talked today about the commutative property and where kids can use it at different ages. It's not that they have to name the property, right? You said that earlier. We're not about naming the property, but that they can use the property and figure it with some relationships.
Cool. The commutative property of addition and multiplication. Who knew? So helpful. We hope you enjoyed our journey today. We love it when you like the podcast and review it. That helps more people see it. Check us out on the website, mathisfigureoutable.com. We'd love for you to join us on #MathStratChat on Wednesday eves for the global number talk. So if you're interested to learn more math and you want to help students become mathematicians where they mathematize their world, then the Math is Figureoutable podcast is for you, because math is figureoutable.